Howdy, today I'm Flipping Science. I'm introducing organic chemistry, looking at combustion of organic compounds, and introducing some of their properties. First understands we're going to look at hydrocarbons are fuels and feedstocks in chemical industries. We need to write equations for combustion of hydrocarbons. We're just going to look at what hydrocarbons are in terms of alkanes and alkenes. This will come a bit later. And we're going to compare melting and boiling points given information. So what is organic chemistry? Organic chemistry is the chemistry of carbon and its compounds. It's the chemistry of living things, and that's why it's kind of organic. Sugars, fats, proteins, DNA, they're all organic compounds. And these are all very important to life. And if you understand organic compounds, that influences things like medicine, because a lot of chemicals used in medicines are organic. Food, health, science, agriculture, there's organic compounds everywhere. So here, for example, this is the compound that makes flamingos pink. So it's an organic compound. It's made up of carbons and hydrogens. So it's very important. So why is organic chemistry important? It's so important that most chemistry departments at universities are broken up into inorganic and organic chemistry. So that gives you an idea. It's basically a division line in half of what chemistry is. That's all based on carbon atoms. And the question is, why carbon? Why is carbon so important? So the reason why carbon is important is because it can make 4 bonds. And what that means is it can bond with 4 other atoms, sometimes fewer if it's sharing double bonds and triple bonds. It can make long chains. It can make structures that are quite large because it's just very easy to add an extra carbon on. It's based on carbons, hydrogens as the backbone, and then we can add in extra atoms as well. So examples, formic acid down here. So we don't really call it formic acid anymore, we call it methanoic acid. It's made of a carbon, hydrogens, and an OH group and a C double bond O group. So it's a carboxylic acid. And this is what stings you if an ant bites you. If we add an extra carbon on top of that and some extra hydrogens, we get acetic acid, which is the basis of vinegar. And if we add another 2 carbons on top of that, so we've still got the same structure at the end. If we add another 2 carbons, we end up with butyric acid, butanoic acid, which is particularly stinky. It smells like vomit and cheese. So we can make long chains, and we can bond with most other atoms, and it's very, very versatile carbon. So it's the basis of organic chemistry. So let's talk about organic compounds. So they're broken up into groups based on their structure and what we call a functional group. So a functional group is something on a hydrocarbon chain that changes the way that the hydrocarbon chain would work. The simplest part of it is a hydrocarbon, so it's just carbons and hydrogens. So they only contain carbon and hydrogen, and you can make really, really long, big, long chains. You can make rings. You can do all kinds of fun things with just hydrocarbon chains. So here's some examples down here. So this is ethane. So ethane is a gas, and it catches on fire quite easily. Down here we have some components of crude oil. So we can have some carbon compounds. This is 1, 2, 3, 4, 5, 6, 7, 8. 7. So that's 7 long, so that's heptane. Heptane is a component of petrol. Diesel, it's a bit longer, and this is why you get more energy out of diesel than you do out of petrol, because you've got more bonds that you can break and reform, and that releases energy that can be then used to power your car. Then we have motor oil, which is really long. Theoretically, it doesn't burn. It's really good as lubrication. And we have plastics. So here's polyethylene. Okay, that would be so polyethylene. So it's just a really long carbon hydrogen chain. That's what it is. And there's different types of plastics. So really we're just changing around what's in here in terms of just adding in functional groups here and there. So what do we use hydrocarbons for? Well, if they're small, we can use them for some uses. If they're larger, we can use them for other uses. But they have a lot of bonds for their size. They're very energy dense because energy is stored in bonds between atoms. Because there's carbons and hydrogens there's lots of bonds for very small molecules. And what that means is you release a lot of energy when you combust them. And we're going to look at that shortly. They're used all over the place. They're used in medicines and plastics and lots of other places too. But one of the main uses we have them is as fuels. So down here is methane. Methane is natural gas. So we use that to cook in our houses, for example. Kerosene is a mixture of hydrocarbons that's a bit longer. So we're looking at 7, 8, 9 carbons long. It's used to power planes. So planes run on kerosene. It's called avgas, but it's mainly kerosene. And then we have petrol. So here we have, this is octane. Octane is one of the major components of petrol. So lots of bonds that you can break, and then when they reform new bonds, they release energy that we can then use to do things like fly a plane, heat your food, or move your car. So we need to go through how to write combustion equations for hydrocarbons. And burning hydrocarbons has made the world what it is today, for better or worse. When you burn something in air, it combines with oxygen. And because you've got lots of carbons in the carbons combined with oxygen to make carbon dioxide. Other products you get are water. So this is assuming complete combustion, and you'll learn next year about incomplete combustion. So you get carbon dioxide and you get water whenever you burn a hydrocarbon in oxygen. You have to do some balancing here, and some of the balancing gets a little bit more complicated when you have even numbered hydrocarbons like we have down here. If we look at methane, so we're burning methane in oxygen, we're getting carbon dioxide and water. And the process that you do to balance is you look at how many carbons you have, and that tells you how many carbon dioxides you get. You look at how many hydrogens you have, and that tells you how many waters you got. So we've got 4 hydrogens here, so we're going to need 2 H2s over here. And then you look at your oxygens and you count up your oxygens and figure out how many oxygen molecules you're going to need over here. This is easy enough if it's an odd numbered hydrocarbon, so methane has 1, so that's an odd number. When it's even, you kind of have to do this doubling so that you get even numbered ratios. The other way you can do it is having fractions, so we'll go through that now. So let's look at propane. So we're going to burn propane in oxygen. So we're going to write out what we've got. Now, the first thing we need to do is be able to read what's in propane. So we have 3 carbons, so 1, 2, 3 carbons, and then we've got 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. So we're going to call it C3H8, and we're burning it with oxygen. And we're going to be producing carbon dioxide and water. Now, the thing that we need to do is do our balancing. So we've got 3 carbons here, so that means we need 3 carbon dioxides. We've got 8 hydrogens here, so that means we need 4 waters. And then we go over to this side and we count up how many oxygens we've got. So we've got 3 times 2 oxygens, so that's 6, plus 4 times 1, 10. So 4 times 1 is 4, plus 6 is 10. So what that means is we then need to go back to our oxygen molecule. To get 10 oxygen atoms, we need 5 oxygen molecules because there's 2 oxygens per molecule. So when it's an odd number, it's fairly easy. When it's a even number, that's when it gets a bit more tricky. So let's look at butane. So butane is the gas found in cigarette lighters, for example. So 1, 2, 3, 4. So we've got 4 carbons, so C4. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So C4H10. We're reacting that with oxygen. And we're going to produce carbon dioxide plus water. Okay, so now we need to do our balancing. So we've got 4 carbons on this side, so we need 4 carbon dioxides over here. We've got 10 hydrogens over here, so we need 5 water molecules over on this side. 5 times 2 is 10, so then we need to look at our oxygens. So we've got 4 times 2 oxygens, that's 8 plus 5. 8 plus 5 is 13, and the problem with that is it's hard to make 13 oxygens over here because this is there's 2 oxygens per molecule of oxygen gas. So we can do this in a couple of ways. What we could do is we could say 13 divided by 2, so that would give us 6.5 oxygen molecules, which gives us 13 oxygen atoms. The other way we could do this is by doubling everything. So if we do 2C4H10, plus, now if we double 13 on 2, we get 13. So 13 oxygens goes to, so double 4, so 8 carbon dioxides, and 10, 5 times 2 is 10 water molecules. So that's 2 ways that you can represent the balancing there for the combustion. The key things are you're producing carbon dioxide and water, and you need to balance so that you get the right numbers of carbon dioxides, waters, and oxygen molecules. Last thing we're going to look at is physical properties of organic compounds in terms of boiling point. And there's basically a rule we need to follow. The longer your carbon chain, the higher the boiling point. And this applies to melting point as well. So if we look at here, these are our alkanes here, and we'll learn what alkanes are in our spoon. The thing we're doing is we're adding extra carbons and hydrogens as we're going down here. So methane has 1 carbon, ethane has 2, propane has 3, butane has 4, pentane has 5, hexane has 6. So as we're getting bigger, our molecules are getting longer. So what that means is that we're going to get stronger dispersion forces acting between the molecules. And the higher, the more dispersion forces you have in terms of the number of electrons that are going to be pulling at one end of the molecule or the other, the stronger your temporary dipoles. And that's why we're seeing this trend in boiling point, where the boiling point is increasing. And this applies for other organic compounds with different functional groups. So we're going to learn about alcohols a bit later on, but alcohols have a hydroxyl group, so an OH group attached to them. But they still have a certain number of carbons attached to them. So methanol has 1 carbon, ethanol has 2 carbons, propanol has 3 carbons, butanol 4, pentanol 5, hexanol 6. So we're still just making the chain longer. And if we make the chain longer, we're adding more atoms, we're adding more electrons, which means temporary dipoles are going to be stronger in partial charge, which means more attraction between the molecules. And we can see that trend there in terms of boiling point. So the rule is the longer the carbon chain, the higher the melting boiling point of the compound. Today on Flipping Science, I introduced organic compounds, looked at their use as fuels, and also talked about some of their properties. That's it for Flipping Science today. See ya.